All right, so we have this last step to do to make this first security notion fully formal, and that is to actually turn this picture into what we'll call experiment notation. So let's do that now. So I'm going to take this picture and turn it into an experiment, and I'm going to actually push this up a little bit. I guess I'm going to be sliding it up and down a bit here to try to make this easy to explain. Okay, so this is all going to be in a bunch of sort of standard notation. So maybe it's good that we're seeing this the first time in video form, so you can go back and look at it repeatedly. So here is our notation. So let's actually turn this into an experiment. Oops, that's not what I want to do. I want to do that. Okay, so this is the key recovery experiment. So we'll write EXP for experiment in the KR or key recovery game, and the object that we're attacking is this E that we've been talking about, this block cipher E, and the adversary's name will generically be A. Okay, let me unpack this again a little bit for you, because this notation, there is some sort of heavy notation you have to get used to at the beginning, and then it becomes very simple to see later on. So what are we doing? We're about to describe the probabilistic experiment for the key recovery game that's being played by an adversary A and attacking the block cipher E. That's what this is. And now what we want to do is to write down a sequence of steps that are in this game, and ultimately we're going to define, as a function of this, is something called the advantage. The advantage of A in the key recovery experiment. The notation for this will be quite similar. This is going to be the advantage, ADV for advantage, in the key recovery experiment, attacking block cipher E, where adversary A is doing the attacking. This will be defined to be the probability that the experiment that we're about to define over here is going to return the value 1, or true. We'll use logical true and value 1 to be equivalent. So it's the probability that this experiment this is the thing that we're ultimately going to want to measure. I'm going to put a box around this because this is a really important piece. Okay. So we're going to take this picture and we're going to turn it into some pseudocode that describes an experiment. That experiment is going to have some randomness in it, which is going to define this probability, and will define the advantage of the adversary A in this key recovery experiment when attacking E as the probability of this. Now, you might be asking yourself, why is it that E is out here and A is inside the parentheses? Well, it's because of this. We'd like to, for any particular block cipher E, we'd like to say, okay, I'm going to fix E. Well, it's AES, let's fix it. And I want to think about just how hard it is to recover the key. So I fixed the key recovery experiment. And now I'd like to be able to say, for any given, if you give me, maybe there's you've come up with 100 different attacks to recover the key against AES. And those attacks are, we'll call them A1, A2, A3, and so on up through A150. You'd like to be able to say what the advantage is of each of those different kinds of attacks, right? So you could write in here A1, and that would be an A1 here. And so then what you're saying is, what's the probability that A1 wins the experiment that we're about to describe? that probability is the advantage of A1. A2, well, that's a different adversary. So this is now an A2, and you're asking what's the probability that A2 wins this experiment, and so on. So what we've really done here, and this is really something powerful, is we started out with this fuzzy idea of I want to know what it means for a block cipher to be secure. We said, okay, let's take as a starting point that it should be hard to recover the key, and we've turned all of that into this. This is actually this advantage. If you think about all of this, everything on the left-hand side of this parentheses, as the name of a function, right? If I were to replace this with just an f, this would be like f of a. This is a function that takes adversaries as inputs and returns to you the probability that that particular adversary wins this game that we're about to describe. And that's cool. We've taken some fuzzy idea of security and turned it into a function that actually measures how well adversaries do at winning this game, at breaking this security notion. This is a hugely powerful thing. And this, in fact, this idea of coming up with mathematically precise functions that measure how well attackers do at breaking crypto systems, this was really the fundamental thing that made the leap from really like 2,000 years of using cryptography, because this cryptography, goes all the way back to Julius Caesar, maybe even before that. Everything that preceded this seminal paper that came out in 1984 by Goldwasser and Macaulay, everything before that paper is sort of ad hoc intuitive crypto. There were no like real ways to measure security of something, no formal ways to measure it. That paper established the idea that no, in fact, we can take a notion like I need it to be hard to recover the key, and I can turn it into something that's mathematically precise that I can now measure. That's a huge thing, because once you have this, man, all kinds of things become possible. So this process is something that we're going to repeat over and over again, of coming up with experiments and advantages for particular kinds of security for a variety of cryptographic objects, be they block ciphers or encryption schemes or hash functions or digital signatures or whatever. Okay, so this is the advantage of a particular adversary A in this experiment that we haven't yet described. So let's actually do the description of the experiment. And all I want to do is I want to take this picture that I've drawn up here, this picture, and I want to turn it into pseudocode. And there's a particular way in which we do that. So we write this down as a sequence of steps, and the steps are run from top to bottom. So the first thing, what's the first thing that happened in this picture above? The first thing that happened, we said, was a key gets picked. So the first thing that happens in the experiment is a key K is picked uniformly at random from the key set, which are keys of length K. That's the first thing that happens. Okay, now let's refer back to the picture. That's the first thing that happens. Then what happens? Well, that key gets put into this oracle box, and the adversary is given access to the oracle and asks queries. And at the end of its run, it outputs some K. So the next thing that happens, there's no more setup, right? This is all of the setup of the experiment. So the next thing is the adversary A runs, and to the standard notation for being given access to an oracle is we write the oracle upstairs, write it up here. So it's given access to an oracle, E sub K, right? That K is this K. That's why we had to pick it first. And we'll often, when we write down an oracle, we'll use this little extra bit of notation, which is parentheses with a dot in the middle. This is to help the reader, as they're reading the experiment, understand that this particular oracle takes one input. It's probably already clear because prior to writing all this down, you would have said what E is, but this is often helpful to write this. So we pick the key, we put that key into the oracle, and the oracle is providing this functionality for E sub K to A. And we suppress the notation of these arrows pointing up to E and down to E. This is just the standard notation for saying that A runs with this oracle, and it's asking queries that are implicit here. And when it's finished running, it outputs a value K prime. And we've said that adversaries themselves are randomized algorithms. So we put this $sign over the top. And I'm going to come back to this in just a second, but I want to finish writing the experiment. So the adversary runs. It runs with oracle access to E sub k. When it's finished running, it outputs a K prime. And I'll write this out in longhand, and we'll shorten it up later. If K prime equals K, then return 1. Otherwise, return 0. There it is. Okay, so this is the key recovery experiment. This is this picture made formal. Maybe I can squeeze this in, sort of, almost. Almost. This is the way that we write down formal probabilistic experiments. So we write the picture down to help us sort of get our bearings, and then we write down what the experiment is in this pseudocode fashion. And this is the way that I'll try to do it throughout the course consistently, and I'd like you to do as well. And once you have an experiment defined, an experiment capturing this picture, then we can talk about the advantage of a particular adversary A in this experiment. Okay? So I said a moment ago that I would comment on this particular arrow with the $sign over it. Now earlier I had said that when the thing on the right-hand side of the sample in the sign operation was a set, then that meant that you sample from this set, unless explicitly said otherwise, you sample uniformly from this set, right? Because I said every set is assumed to be equipped with a distribution, and implicitly that distribution is uniform unless said otherwise. This actually means exactly the same thing. If you think about it, the adversary is running, and it's flipping coins as it runs, potentially, and it's asking these queries. We can think about the outputs, the possible outputs of A when given oracle access to this. There's some set of outputs that it can, in fact, the set of potential outputs is the entire key set, right? Any execution of the adversary as it flips its coins and asks its oracle queries, any execution induces a distribution over the possible outputs that it can produce, right? If I were to fix the coins, let's say that A doesn't flip any coins at all. It just asks oracle queries. It's a deterministic procedure. Then, for any set of query responses that it sees, there's a particular value of K prime that it outputs. Okay. Now, if A, so the distribution is the simple one, right? It's basically fully determined because there are no coins being flipped. Now, if A is flipping coins internally, then there is a distribution that's induced over the possible outputs, and that distribution is determined by the coins that A flips. So this value that this thing will take on ultimately, this is a very complicated random variable. This is a very simple random variable here. That's the uniform random variable over this set. This is a very complicated random variable, a very complicated distribution over this set. So this notation here, it still means to sample from the thing on the right-hand side according to its distribution and to assign the value to K prime. But the distribution by which the sampling is done is extremely complicated, and it depends entirely on what A's strategy is for, say, making oracle queries and for picking this final value, and the coins that it flips. We don't know what this distribution is over the outputs, but we don't care. What we're saying is simply run A, let it flip whatever coins it wants. So you can think of when the thing on the right-hand side is an algorithm, you can think of this as being like a reminder that this thing is flipping coins. Run A, let it flip whatever coins it wants, let it ask the oracle queries it wants, and then that induces a distribution on the possible outputs that it can make. So really this notation is exactly the same in these two settings. It's just you have to think of this thing as being a set of possible outputs. Okay, so there's our experiment. Key is picked, A runs, asks oracle queries, flips coins, outputs a k prime, and it wins if k equals k prime, and that's exactly the case in which the experiment outputs 1. And now we can say, what is the probability? So, I said that this is a random variable. In fact, this thing here, the value of this, which is either 1 or 0, this too is itself a random variable, which is why we can talk about the probability of it. It's, again, an extremely complicated random variable because it depends not only on the randomness of picking this key, but it depends on the randomness that's used inside this adversary. So the probability that this thing outputs 1 is a function of the coins that are used here. This is always the first thing you should do when you see an advantage statement. You should be able to look at the experiment over which this advantage is defined and see exactly where the probability is coming from, right? In fact, anytime you see in any class somebody write down PR and then some brackets or parentheses and then something inside, you should always ask yourself, probability over what? What random choices? And here the random choices are the selection of the key and whatever coins A flips as it runs. So there it is. This is our first fully defined security notion. This is the key recovery security notion, and this is completely formal. This is I wanted to write this in yellow. This is formal notion of key recovery security. And that's really something to ponder on because this is a huge thing. This is the first time, I'm guessing, probably in your entire experience of thinking about cryptography, that you can actually start to formally argue about the security of a particular block cipher against attackers that try to recover the key. Well, so there's one last detail to pick up here, and we said we want to measure the probability of the adversary winning this game, guessing the key, as a function of Q and T. So anytime that we write down an advantage measure like this, there are resources that we'll keep track of. So resources of the adversary. By resources, we mean, in this particular case, the information and computational resources. So the resources of Q these are the things that you want to track because as they go up or down, they definitely affect the value of this probability. So the resources of Q in this experiment, the resources of A in this experiment are 1, the number of queries, Q, and 2, the running time, or the time complexity, as it's also said, the time complexity, T of A. So this is the number of queries Q asked by A, and this is the time complexity, T of A. And the reason we keep track of these things is because when we get a little bit more mature in this process, we'll actually be making arguments about what is the probability of experiments like the one that we just wrote down, and we'll be able to really write down an upper bound. We'll be able to write things like this thing is always less than or equal to, I don't know, make up something over here, Q squared over 2 to the n plus T over 2 to the k. As an example, we'll be making statements like this. We'll be proving, mathematically proving statements like this, that an adversary A that uses Q queries and runs in time complexity T has advantage of winning this experiment, in other words, of recovering the key, that is at most q squared, so the number of queries squared, divided by 2 to the n, where n is the n that's in this block cipher E, so think about like 128, and plus t, the time complexity of the adversary, over 2 to the k, where k is the size of the key. This is another time to stop and really appreciate what has happened when you can make such a statement. This says that, well, once I fix n and k to be, say in the case of AES, these are each 128. This tells me immediately, if I want this number over here to be small, notice that this is always going to be a number between 0 and 1 inclusive, right? Because it's a probability. But really, you want to say that the advantage is small. You want it to be hard, right? You want it to be hard to recover the key. And that's exactly what's being captured here. If the probability of the adversary causing this experiment to output 1 is small, then that says that almost all the time the experiment outputs 0. And the experiment outputs 0 when the adversary does not guess the key. So a small advantage in the key recovery experiment is effectively saying it's hard to recover the key. So this is, if you can write a bound down like this, and again, this is a fictitious bound, we haven't proven this, I'm writing this as an example. If these are each 128, then what we're saying is this advantage is going to remain small until Q, the number of queries asked, which you can think about in an encryption scheme. Think back to that picture of ECB mode or of CBC mode. Each of those queries is going to somehow correspond to a block of plain text going into the block cipher. So until the number of blocks that go into the block cipher is something like, well, I want to make this number something close to 1, because if I'm saying the attacker is doing well, this number is close to 1 when Q is roughly the square root of 2 to the n. And if n is 128, that means when Q is around 2 to the 64. So once Q grows to be around 2 to the 64, in other words, when around 2 to the 64 blocks have been processed, then this number becomes something close to 1. But until that point, this number here is quite small. If you only allow the attacker to be able to see, say, 2 to the 32, or even 2 to the 20, say 2 to the 20 is a million, right? If Q is 2 to the 20, this is the most number of blocks that it'll see under a particular key, then Q squared is 2 to the 40, and I'm dividing that by 2 to the 128. So this is, what is 128 minus 40 is 80 something? Oh, can't do arithmetic. This is, by the way, this is a law of teaching, is that the closer you are to the whiteboard, or in this case to the screen where I'm making this video, the dumber you are, and this will bear itself out repeatedly. In any case, you got 2 to the 40 divided by 2 to the 128. That is 2 to the minus 76, right? 1 over 2 to the 76. So when you're allowed to ask a million queries, this would say this term is 1 over 2 to the 76, which is, again, infinitesimally small. Likewise, this term, if this is going to dominate, then that means that t has to be on the order of 2 to the k. But k, in the case of AES, is 128. We're just saying you need to have time complexity on the order of 2 to the 128 steps. So having this bound on the right-hand side has just told you that so long as you don't have attackers that run for something like 2 to the 128 steps, and you don't let them see something like 2 to the 64 input-output pairs, this number on the right-hand side is going to be small, which is saying that the attacker that is allowed to ask, say, a million queries and run for a day on a modern computer is not going to recover the key. This number is going to remain small. And that, friends, is one of the real beautiful points of modern cryptography, is the fact that we actually started with this idea of what does it mean for a block cipher to be secure? And we ended up with this bound, fictitious mind you, that tells us, as a function of the number of blocks of plain text that are processed and the running time of the attack, it tells us exactly how well an adversary can do at recovering the key. That is phenomenal. It really is. And maybe it sounds like I'm overselling it now. And if I was in class, I'd really be making a lot of show about this. and you'd be chuckling at how much I made, because it is such a cool thing that you will come to appreciate. Okay, one more thing about this, then I'll stop my, I'll get off my soapbox. These are the resources we track. Now, I've said that this advantage is for a particular adversary A. So as soon as we write down a particular attack, then I can talk about what's the advantage of that attack by plugging that A into this experiment. Mind you, the A that's here is this A, right? So whatever adversary you specify, this is it. Well, if you give me an adversary that asks a million queries and runs for 2 to the 40 steps, say, you can ask the question, is that the best adversary? Is that the best key recovery attacker that asks a million queries and runs for 2 to the 40 steps? We'd like to be able to say, make positive security statements about how well the best attacker is with a given set of resources. And so we sort of overload this notation. We define this is called the resource parameterized advantage. The advantage against E in the key recovery experiment. But now instead of having a function of an adversary, we have a function of the resources, Q and T, to be the max over all adversaries A, and I'll specify this A in a moment, of the advantage of A against E. Oops, that's an E in the key recovery experiment, where the max is over all A that have resources Q and T. So this is the resource parameterized advantage. This probably deserves its own box as well. The resource parameterized advantage. So if you can upper bound this quantity by something like this, then you really are saying that the best possible, right? This is the maximum advantage of any A that uses Q and T. So if I can upper bound this thing by this, then I'm saying no matter what adversary you give me, I don't care what the particular details are of the attack, if it uses Q queries and running time T, it can't do better than this at winning the game. So this resource parameterized advantage is a nice thing to have too. And when we make security statements, we'll sort of move back and forth between these two things. It'll usually be this kind of a statement that we make for a particular A that we'll describe, but we'll often generalize to this. Okay, wow, we have covered a lot of ground today, and I think maybe it's worth doing just one more thing to kind of exercise this new power that we have, of coming up with formal security notions. In particular, after we take a break, let's actually try to specify an attack A and drop it in here and see what kind of advantage that attack will get. Okay, before we do what I said we were just going to do, I did want to point something out, and that is that all of this discussion so far has been about block ciphers, and naturally, because that's sort of the unit of the course that we're in, and we've established this first notion of security, this key recovery notion of security. But I don't want to give you the impression that this is a security notion that only applies to block ciphers. So here, I've written down. Let's let F be a function family that just has keys from some key set calligraphic K and inputs from some set D and outputs things in some set R. It's just some function family, not necessarily a block cipher. In fact, F could be the function that on every input D, it just outputs its key K, right? That's assuming that the the range and the set of keys are the same thing, so if R was calligraphic K, then that's a totally valid function family to think about. It wouldn't be a very good one from the perspective of key recovery, of course, but it is a function. So the point I wanted to make is that you can have some arbitrary function family. It's not necessarily a block cipher, and we can still talk about the key recovery security of that function family. I realized that as I was sitting here thinking about the fact that in this first line I'm saying pick a key from this particular set. But the only reason it's picked from this particular set is because that's the set of keys for this object E that's under consideration in this experiment. If we had a different object, say this F that we were considering, then necessarily this first line needs to change. The fact that the first thing that happens in the experiment is a key getting picked doesn't change the order of experiment. Essentially the topology, right, of what we wrote down here doesn't change. It's just the particulars. So in particular, the key gets picked from this set, which is the key sets of this, right? That the particular set will be determined by what is the object that's under attack. So that has to change. And of course, then up here, the adversary was given oracle access to E under some key K. Here, it's given access to F under some key K. Nothing else changes. But the point I wanted to make is that the key recovery experiment is not something that is particular to block ciphers. It can be extended to function families. And in fact, typically when we write down security definitions as we go on, we'll be thinking about them quite generically, even though we may have specific uses in mind. Like here, we're specifically thinking about recovering the key of a block cipher. The notion itself is agnostic to whether the thing that's being attacked is a block cipher or not. Okay, enough about that. So what I want to do now is to think about this advantage just a little bit. I'd like to say something about what is the advantage of a particular attacker in this experiment. So let's do that. Let's see if I can, how much room do I have left if I scroll up here? Lots of room, good, okay. So I want to give a particular attacker. So let's give a particular key recovery attack and see what its advantage is. Okay, the particular attack I want to give is well, let's give a couple. Let's give a stupid one first. So this will allow us to introduce this notation that I'll be wanting you to use in the class. To describe an attack, attacks are adversaries. So let's do that. Let's describe adversary A. Adversary A. This is the way we'll start this. Now what we want to do is, just like we did in the experiment, we want to give the list of steps that adversary A carries out. So adversary A is going to be given access to an oracle, right? And the adversary, how to say this without being overly vague. We know that in this particular experiment, the oracle that the adversary given is this one. It's E sub k, right? The algorithm itself, and this will become more clear when we have more complicated security notions, in a sense, doesn't know what it's been connected to. It has some oracle input-output port, and something has been connected to it, and it can be programmed so that it only asks n-bit strings on this output port, and it expects to get n-bit strings on the resulting input port. But you can take the A that's here, and you could have connected any oracle to it that will take in n-bit strings and returns n-bit strings. It didn't have to be this one. Of course it will be. I'm sorry if that all sounds pretty vague, but it will get clear the more we look at these. So in any case, we want to say that the adversary takes exactly one oracle, and since generically we don't know, I mean, this A could be used to attack F, it could be used to attack E, it could be used to attack something else. So what we do, instead of saying that A is specifically getting access to something called E, we just say it's getting some generic oracle, and we often will do the oracle as like kind of a calligraphic O for oracle. So this is just saying adversary A is expecting some oracle O, and we'll make reference to this oracle in the code. And then when this A is actually dropped into, say, this experiment here, this oracle is now instantiated. Yeah, it's instantiated by this thing. But the code of the adversary is agnostic to what the particular oracle is. It just knows I get to ask this oracle something of a particular kind, and I get back stuff from the oracle. So writing it like this allows us to say that this adversary is sort of agnostic to how the oracle itself is instantiated. Okay, so what do we know? Let's make a really stupid adversary. Ready? Let's do this. Adversary A just does this. It samples K prime uniformly from, well, we know what the key set is. Yeah, I'm going to sort of contradict myself here, I guess. I just want to have an adversary that picks a key uniformly at random, and it has to pick it from the right set. So we're assuming that A actually knows what the correct set is, and that in this case O is E K. We know that the key should come from the set 0, 1 to K, or K-bit strings. So what does this adversary do? It picks a K prime and it returns it. That's it. That's the entire adversary. Yeah. All these experiments use these pseudocode. They end as soon as the first return statement is hit, and the return statements thus always are the last things that are there. That's it. That's the entire adversary. So let's give this thing a name. This is adversary. We call this adversary dumb. This is our dumb adversary, right? What does it do? It doesn't ask a single query. In fact, we never even had to say all that gibberish about this thing up here. Adversary dumb. Just as soon as it is told to run, it picks a key and it returns it. Well, we can ask, what is the advantage? What is the advantage in the key recovery experiment attacking E of this particular adversary A? What is it? Well, it's 1 over 2 to the K. Why is it that? Well, by the arguments that we gave, I think, a couple times already earlier in this lecture, and that is that what happens? So we have to unpack this. What is this? The advantage is the probability that the particular A, so I should have written this down here. So let me correct this, and then I'll say what I was about to say. This isn't. I made a syntax error here. This A is in particular the dumb A. What's the advantage that A dumb gets? Okay, so if we go up here and this is the probability that A dumb wins this experiment. So then I look over here at the code and say, okay, this A is now A dumb. So this is A dumb, right? And what happens in the experiment? The key is picked uniformly at random from the key set. A dumb runs. What does A dumb do? Well, we just described what A dumb does. It picks a key, K prime uniformly at random, and returns it. So that K prime is this value. Now, what's the probability that that randomly chosen K prime is this randomly chosen K prime? It's exactly 1 and 2 to the K because this selection was uniform. In fact, we could have made A dumb even more dumb. Ready? Let's make an A dumber. Here's A dumber. A dumber does this. Return 0 to the k. That's it. One step. No, it's not even a randomized algorithm, right? It's completely deterministic. As soon as it runs, it outputs this value. Well, what's the advantage of A dumber in that game? It's still 1 over 2 to the k. Why? Because the key that was picked in the experiment was picked uniformly at random, and the chance that that key is 0 to the k is 1 and 2 to the n. So the advantage that this A gets and the previous A dum gets is exactly the same. But this is already pointing out the fact that A dumber and A dum, which picked k prime uniformly at random, those definitely were different adversaries. And yet this advantage let us talk about the probability of those two adversaries being able to win. Now, it happens that their advantage is exactly the same, but this is just highlighting in a very simple way the fact that the advantage is a function that takes adversaries as inputs and outputs a real number between 0 and 1. Okay, let's try to be a bit more smart then. Let's not just do this. So let's not be so harsh. We're going to make up a new adversary A and ask what its advantage is going to be. So how about this adversary? Yeah, let's do this. Sure, why not? I'm not actually sure where this is going to go, but let's give it a shot anyway. Let's make up a new adversary, and we'll just call it A generically. So what does this adversary A do? We have to describe the steps. We know it has to run. It has to potentially ask some oracle queries, and it has to output a guess at the key. So let's do this. Let's have it start by ask 0 to the n to O and receive y in return. Okay, that's step 1. And this is a totally fine way. You can make this more, mathematically precise. In fact, if you wanted to really compact this down, you would write this like this. Y gets cal 0 of 0 to the n. This is really the nice compact way, and I'd prefer to see this because I understand completely what this means. This means that I'm asking the oracle that was generically named here, the value 0 to the n, and the resulting value is assigned to y. But this is also totally fine. If you're not fully comfortable with this and you want to just say what it is you're doing, that's totally okay too for now. So let's ask O, our oracle, the value 0 to the n, we get y in return. And then what I want to do, let's try this. For each k in the key set, which in this case is 0, 1 to the k. It looks like a k there, which it's not. Or each. For each k in the key sets, I want you to do the following. Y prime gets E sub, maybe I should be careful here, let's call this K prime. For each K prime in the key set, E sub K prime of 0 to the n. So what are we doing? We're saying this is a for loop, right? For each K prime in this set, of which there will be 2 to the K, I don't care how you enumerate this loop, but for each of these you're going to do the following things. You locally compute this E sub K prime. Why can you do this? Because, as we've said before, the adversary always is assumed to know all the algorithms. It just doesn't know what the secret keys are. So it can compute this locally, right? If this is like AES, this is AES under some key K prime, which we've just picked inside of our for loop. And we're just computing what's the output of AES under that key when I ask it 0 to the n, and we assign that value to Y prime. What do we want to do? Well, we want to use this to help us determine whether or not well, to help us guess what the key is. So if what? If y prime equals y. In other words, if the value we compute locally matches the value that we got back from the oracle, then well, there's a simple way and then there's a more complicated way. Let me give the slightly more complicated thing because it'll allow us to talk about this later in some more detail. So if the y that we compute locally matches the y we got back from the oracle, then let's add let's take some set S and let's add to it. This is some more notation, I guess. And S gets S union with this value k. And so now that means I need up here a set. So let me stick up in here. Let's initialize S to the empty set. S initially gets the empty set. So I've got some set S that's initially empty, and then for each key k, I'm doing this. I'm computing locally, and then I am running this check. If the locally computed y matches the one returned from the oracle, then I take the key, the k prime, sorry, and I add it to this set. And I do this for all of these. Yeah. Okay. So when that loop is finished, then what happens? I've gone through all of the keys. I'm performing what's called exhaustive key search, right? So maybe we can give this guy a name since we know what it's doing now, EKS. Exhaustive key search. It does this loop over all possible values of k prime. At the end, it has some set S. So this set S, what's in this set S? It's all the keys k prime such that 0 to the n, when computed under k prime, maps to the same value y that was returned by the oracle. Now we know that the oracle has an e sub k in it, which means there is some key k that maps 0 to the n to this value of y. This loop will find all keys k that map 0 to the n to this particular value of y that we've seen. Now, as I've said before, there could be more than one, but we'll definitely have all of them, and one of them is this one. So what should we do? We have to actually return a k prime, right? There's some statement at the end here, which is return some value. Let's give it, maybe call it k star. And this is the value we're going to return. And how are we going to choose it? Well, we definitely want to choose it from among the elements that are in this set S, because these are all of the keys that explain 0 to the n mapping to y. And I don't know, there are various ways to do this, but I think maybe the easiest thing to do is just pick one of them randomly. So let's let k star be assigned a uniform element from the set S and return that value. That's our adversary. So this adversary is mounting an exhaustive key search to find all of the keys that can explain this mapping, and then it picks among the keys that are there. We know for a fact that this set S will not be empty because it will have to contain at least this key k in it. If we're lucky and S only contains that key k, then we're guaranteed that this k star is in fact the correct secret key, and we're definitely going to win. If S is bigger than 1, if S cardinality more than 1, well, then it might be one of them, right? In fact, what's the probability that we win? Well, it depends on the cardinality of S. So let's in fact see if we can work this out. We'd like to know now, what is the advantage? I guess I can stick in this. What is the advantage? Right over here. I want to know what's the advantage. In the key recovery experiment, attacking E of adversary A, EKS. That's what we want to answer. Well, we know it's the probability that the adversary wins this experiment. So again, we go back to the experiment. The A that's in this experiment now is our exhaustive key search adversary. So this is like, I'm harping on this point because this is a mistake that people make often. The experiment itself is defined in terms of some generic adversary A. We have to name this something because it's going to appear in the code. When we actually think about the key recovery experiment for a particular A, then that particular A, in this case, it's the exhaustive key search experiment, is the A that's here, right? So please don't be confused about that. This A that's written in the statement of the experiment is just some generic placeholder A. All right, so the A that's running here now is the exhaustive key search adversary. So in answering this question, in this question here, we know that we're actually thinking about the key recovery experiment of this particular EKS adversary. This is the thing that we need to think about. All right, so what happens in that experiment? We just go back and look at our experiment. The first thing that happens is this secret key is picked uniformly at random. It's put up in this oracle. What does our adversary EKS do? It asks 0 to the end of this oracle. It gets back a Y. And now it sets offline. And it outputs some value that in the experiment we're calling K prime. Now maybe it was an unfortunate notational class that I'm using K prime here as well, but don't confuse the K prime that's in here with the K prime. Whoa, that's not what I wanted to do. With the K prime that is up here, right? When you're looking at these things, well, okay, we're computer scientists, think about these variables as having local scope, right? This K prime is locally scoped up here. The value that's assigned to K prime in this experiment is whatever the value is that's output by this. And we've chosen to name that in our code for A, K star. So this K star is the K prime in the experiment. All right, so the adversary asks this one query, and it's trying to guess this uniformly random key. We know that that key is somewhere in this set, and the adversary picks one of those by sampling uniformly from S, and we'd like to know what's the probability that adversary A actually outputs the correct value of S. Sorry, the correct value from S. And we know that K is in this. So we know that S equals, well, we know that the particular secret key K is in here. Maybe it's even worth writing that in a different color because that's the one that we're really after. So we know that the secret key K is in here, but there may be other things in here too, right? There's, I don't know, some K 0 and some maybe K 15 in some enumeration of the keys, maybe K 11256 is in here, and so on. Right? There's some number of keys that are in here. We know that somewhere in here is the particular K that we're after, the K that's in the oracle. All right, so when we finish this loop, S looks like this. The key that we want is in here. We pick one of those uniformly at random, we put it to K star, and that's what we return. And so what's the probability that the one that we return is actually the key that was in the oracle? It's exactly the probability that when we sample uniformly from this set, we pick this one. So the probability that we win, the probability that we win this experiment is what? It's 1 over the size of S. That's the probability. That's the advantage of the adversary. 1 over the size of S, where S is the size of this set. So if we can find a way to reason about how big that set is, then we'll be able to say exactly what is the advantage of this particular attack. So let's take, for example, almost at the bottom here, let's say, so for example, say the size of S equals 2, right? In this run here, which, by the way, what's sort of the rough order of complexity of this search? This is roughly 2 to the k operations or work, if you like. So this is essentially going to dominate the time complexity of this adversary, right? Everything else is, when you ask a query to an oracle, that's assumed to be a unit time thing, so that's 1 unit of time. Then there are 2 to the k units of time essentially that are used for this, and for sampling we can also think of as being unit time, but whatever our convention is for sampling, it's definitely going to be dominated by this. So this is roughly a 2 to the k time complexity attack, and if that attack yields exactly 2 keys, right? There were 2 keys that explained 0 to the n mapping to y, then that implies that the advantage in the key recovery experiment of this particular EKS is 1/2, right? And that's actually really good, because the largest number that this can be is 1. Right, the smallest is 0, and we've said that if we have, a really dumb adversary, then this number is not 1/2. It's 1 over 2 to the whatever 128, right? This is bearing out what I said earlier, that if in fact it's the case that the number of keys that explains a particular input-output pair is small, then this exhaustive key search attack, it expends an exponential amount of time, but it does really well. Yeah, it gets advantage 1/2. And advantage 1/2 at guessing the key, that's really good. Half the time you've guessed the key, and now you can decrypt anything that you want. So what we want, of course, is for this number to be small. If we're security designers, if we're attackers, then we want this number to be big. And so this attack does really well. And in fact, we won't do it in this lecture because this lecture is already quite long. But we can do some heuristic reasoning and argue that if E is in fact what we'll call an ideal cipher, which is a block cipher that behaves in the most ideal way that it can for every key, then the size of this set is going to be something like 1 or 2, and it's actually a function of this of k, the key length, and n, the block size. But for realistic values of k and n, like when they're each 128, in fact, when they're each 128, this value is going to be 1. So this value is always going to be quite small. And so what this is telling you, again, it's harping on the same point that I did before, this is telling you, look, if you've given me a block cipher for which there are very few keys that actually explain 0 mapping to any particular point y, then if I'm willing to expend an exponential amount of time, I'm going to win. I'm going to guess the key. Now, what does that actually tell you? Well, okay, so what happens? I've expended an exponential amount of time. So this really isn't saying anything bad about your block cipher design. It's saying that, yep, if you let me run for the amount of time it takes to search the entire key space, I'll find it. Of course, that tells you, well, I need to make the key space pretty big then. And this, again, is intuitive, and it's being captured here. If the key space, let's say you have a block cipher that has 4-bit keys, well, how many keys are there then? 2 to the 4, which is 16. So then that's saying, okay, well, if you give me a 4-bit 4-bit keys in a block cipher, I'm just going to mount the exhaustive key search, and I'm going to win. Which is, of course, intuitive, right? So this tells you I need to have to defend against, to have any hope of defending against exhaustive key search attacks, I'm going to have a key that's sufficiently long. So this, in fact, is giving you some useful engineering input. Yeah, this is a payoff of having gone through the process of coming up with a formal notion of security for key recovery security. It's telling you precisely, look, if you want me to have a good probability of winning, then make the key size small. If you want to avoid at least this attack, now mind you, I'm not ruling out any other kinds of key recovery attacks. I'm just saying if you want to rule out exhaustive key search being able to work in a reasonable amount of time, you're going to have to make k big, right? If I make k equal to 128, then what this result is telling you is if you let me make an adversary that can run for something like 2 to the 128 steps, which, by the way, nothing is ever going to run for that many steps, then I'm going to break your cipher because I'm going to find the key. If we change this slightly, if we didn't say for each k prime, if we said for, I need a value here, for alpha values of k prime. So let's say I make up a list. I pick alpha values uniformly at random from this set, and I just run this test for those alpha values of k prime. Well, I haven't done an exhaustive key search. I've only searched a portion of the space. In fact, I've searched an alpha fraction of that space. Then I'll still have some probability of winning, but it's now harder to say. You can say, if you do this on some paper and you're comfortable with probability, you can figure it out for yourself. But if I only search an alpha fraction of this space, then conditioned on actually trying one of the keys that is this key, then I know that the key will appear in this set, and I'm back to this thing. Conditioned on that. Conditioned on not having among those alpha keys k prime this particular key, then the chance of me actually outputting the correct, of this adversary outputting the correct key is 0, right? So then that means that the probability of outputting the correct key in that case is going to be this times this fraction alpha, which is the probability that, so what is this, alpha over 2 to the k, right? It's the probability that in the alpha attempts, the alpha random picks of k prime that you're going to try, that one of those is this. Conditioned on that happening, then the chance that you actually win is 1 over the size of all the keys that could explain, one of which is the correct key because we've conditioned on that. So this gives you an idea of what's the probability of guessing the key if I mount an attack where I don't do an exhaustive search, but I do like sort of a randomly punctured search of the whole key space. It's roughly, assuming that this is small, if this was like 2, then the probability of that punctured random key search space is going to be alpha over 2 to the k plus 1, right, when this is 2. That's telling you sort of what we were thinking about earlier when I was saying there might be this like t over 2 to the k term. If each time through this loop is costing you effectively 1 unit of time, and you've done that loop alpha times, then alpha is roughly the time resource t. So this is saying if I do a punctured search, then the probability of winning is something like t over 2 to the k. So again, this is teasing out for you the fact that the probability of winning by exhaustive key search is fully determined by how many times you're willing to do this loop test here, which is completely intuitive, and yet what we're doing is capturing it formally. Okay, so right, I think that's plenty for this lecture. In fact, it's probably more than I would have been able to do had we actually been in class together for this lecture. There's one more thing I want to do next time, which is to actually try to argue for you that this number will be small. On average, this value will be small, but that's going to require us to do a bit extra work here. And then what I want to do is argue for you that in fact this notion, this key recovery notion is, oops, let me pull back here and move this around a bit. Yeah, that this notion that we've established here, this was a great process. Doing this was super useful for us because this is the process that we're going to do over and over again of going through a picture and then writing down an experiment and establishing what the advantage is based on that experiment. So we did all this, and this was super useful because we'll keep doing it. But I will tell you that, in fact, this kind of security against key recovery, is not sufficient for cryptographic use. It's definitely going to be necessary because, as we've said, if you can't protect yourself against having the key being recovered, then any kind of security, all bets are off because the key is now out. But so it's necessary, but it's not going to be sufficient for what we're going to want to do. Because what we're going to want to do is make arguments of the following form. Here is CBC mode encryption. And what I'd like to be able to say is the following. Once I define a security notion for an encryption scheme, period, and then I instantiate that encryption scheme with CBC mode, which is depicted here, I'd like to be able to say that the security of CBC mode relative to the security notion that we've defined for encryption reduces to the security of the underlying block cipher that's used. Let me say that again. We want to say that the security of the encryption scheme as a whole reduces to the security of the underlying block cipher that's being used. Why do we want to say that? Because if we turn that on its head, that says if you have an algorithm that can attack the encryption scheme and does well, so it violates the security property of the encryption scheme with high probability without using an exponential number of queries in an exponential amount of time, the existence of an attack on the encryption scheme will imply the existence of an efficient attack, meaning one that doesn't ask a whole lot of queries or run for exponential time, on the underlying block cipher. Thus, if you can prove or you're willing to assume that the block cipher does not admit efficient attacks, it cannot be the case that the encryption scheme admits efficient attacks. Go back and listen to me say that again, because this is where we're going with this. We want security notions for underlying primitives like block ciphers that are sufficiently strong in some sense to support statements of the form, if my block cipher is secure relative to a given notion, then the thing that I've constructed out of it is also secure relative to its security notion. And so when I say that the key recovery notion is not going to be sufficient to make those kinds of statements, what I'm saying is that we'll be able to argue, to give examples of block ciphers which are very secure against key recovery attacks. And yet, if you put them into an encryption scheme, the encryption scheme would be broken, trivially. So key recovery security is not going to be sufficient for the kinds of statements that we want to make, but it is a good first step. So I'm glad we did this today, and next time, depending on how I feel about what's been covered here and the questions that I get, we'll either continue on with thinking about the key recovery advantage and trying to argue, at least in some model, that the size of that set of consistent keys S is typically small. Or we'll just move on and say, okay, key recovery wasn't in fact what we want, and we'll say why, and then we'll move on to a security notion that is what we're going to want. And we'll be able to argue that that security notion, if you meet it, you're already going to meet this one too. So that's all coming up in some order in the next lecture or so.